Welcome to AP Chemistry at Hananiga. Of notes from Chapter 17 dealing with Section 4 and the first half of Section 5. And what 17.4 deals with is what's called solubility equilibrium. And you may remember from honors chemistry that is KSP. Now, really, what we're looking at is an equilibrium system of low solubility salts. If you have an ionic compound that has a very low water solubility, when you drop it in water, you very quickly reach saturation, which means you've reached an equilibrium situation. The saturated solution has an equilibrium because the rate of dissolving is equal to the rate of recrystallization. So it looks like it's not doing anything, but it's continuously dissolving and continuously recrystallizing at the same rate. That's equilibrium. So KSP is looking at the equilibrium system of a low solubility salt. Now, if we write the equilibrium expression for that reaction, it was Ba times the concentration of SO4 2 minus. Notice the barium sulfate's not in the equilibrium expression because that was a solid. And notice we're calling the K here KSP. It means the solubility product, because that's what we're doing is multiplying solubilities here. And it's a way to look at equilibrium conditions created by dissolving a solid in water that has a low solubility. So what's the KSP of calcium hydroxide if a saturated solution has a concentration of 0.012 molar. Now the first thing you have to do is write the equilibrium reaction that we're talking about. Now you're going to take and put the solid calcium hydroxide on the left, and you're going to, as a low solubility substance, very quickly establish equilibrium when you reach saturation, and that's going to be dissolving in equilibrium to form calcium ions and 2 hydroxide ions. And once again, it's going to start in its solid form, so when we write the equilibrium expression, the calcium hydroxide solid is not in the equilibrium expression. So we end up with the concentration of Ca2 plus times the concentration of OH minus squared. Remember, we always raise it to the power of its coefficient, and the coefficient in front of the hydroxide is 2. Now, in this particular case, it gives us the saturated concentration of the calcium hydroxide. So at saturation, it's 0.012 molar. Well, if the calcium hydroxide is 0.012, then the calcium is 0.012. It's a 1-to-1 stoichiometry here. And the hydroxide would be twice that. So there's a direct relationship between the molar solubility here and the concentrations of the ions. And most importantly, between the concentration of the cation and the anion here. The cation is going to be half of what the anion is, or the anion, OH minus, is going to be twice the concentration of the calcium. So if the calcium is 0.012, then the hydroxide is 0.024. And remember, in the equilibrium expression, that 0.024 is squared. So we end up with a KSP of 6.9 times 10 to the negative 6. And notice, that's a very small number. That means it's a heavily reactant-dominated reaction, which means it's not very soluble. And in general, the larger the negative value there, so the smaller your KSP is, in general, the smaller your solubility is. Now, KSP is not the same as the solubility. It's the solubility product constant. But if we know the KSP and we're forming this system by dissolving the solid in water, from the KSP we'd actually determine the molar solubility as well as the actual solubility of the substance. Now, be careful. Molar solubility and solubility are different. Molar solubility is moles per liter. The solubility is grams per liter. And then we also have a relationship with the concentration of the ions at saturation, and that's all related to each other as well as to the KSP. So we're going to look at the relationship between these. So here's a problem. If the KSP of calcium hydroxide is 6.9 times 10 to the negative 6, we just established that in the last problem, calculate the solubility of calcium hydroxide in grams per liter. Well, we start with our equilibrium reaction. Write that as an equilibrium expression. In this case, it's going to be a KSP. And remember, we set up icebox. And remember, as a solid, this is not going to appear in the expression. Now, before any calcium hydroxide dissolves, zero hydroxide. But as it starts to dissolve, the concentrations of the calcium and the OH are going to go up. Now, based on the solubility, or I should say, based on the stoichiometry, if the calcium increases by a certain amount, the hydroxide is going to increase by double that. Now, normally when we set up icebox, we're going to put X's here. In this case, I'm going to use an S, and you'll see why in a second. So as the substance dissolves and reaches saturation, whatever the concentration of the calcium is, the concentration of the hydroxide has to be double that. So at equilibrium, the calcium would be S and the hydroxide would be 2S. If we substitute into our equilibrium expression, the KSP in terms of solubility, or S at equilibrium, because that's what that S actually stands for, is the molar solubility, we get S times the quantity of 2S squared, which means S times 4S squared, which gives us 4S cubed. If we divide by 4 and take the cube root, we find out S, which is the molar solubility of the substance, is 1.19 times 10 to the negative second molar. So that would be our solubility of the substance. But it didn't, or I should say, that would be our molar solubility, which is what S represents here. And remember, this S relationship, that in this case, the KSP has to equal 4S cubed, is always going to be true when we're forming the equilibrium system by dissolving the solid in water. There's a direct relationship between the concentration of the ions at equilibrium as well as the solubility and molar solubility in the KSP. Now, it asks for solubility, which would be grams per liter. So all we do is take our molar solubility and convert it into grams per liter using the molar mass and dimensional analysis. So in this case, to 2 sig figs, we end up with a solubility of 0.89 grams per liter if our molar solubility was 1.2 times 10 to the negative second molar. So that's the relationship between solubility and the concentration of the ions, the KSP, as well as the solubility. Now, 17.5 gets into what affects the solubility of low solubility substances. And we're going to look at the first two in 17.5, and we're going to save the last one for the next set of notes. So how does common ion effect affect our solubility, and how does pH potentially affect the solubility if we have active cations and anions on our product side in our dissolving? Well, first, common ion effect. Remember, the common ion effect was a Le Chatelier's principle situation. If we add a common ion that contributes either barium or sulfate, that's going to shift equilibrium to the left, which fundamentally means less is dissolving. And if we knew mathematically how much barium or sulfate we were adding and we knew the KSP, we could actually set up an icebox problem and determine what the concentration of the other substance was. But fundamentally, what you need to know here from a conceptual point of view is that by the common ion effect, if I add a common ion from a salt, I'm decreasing the solubility as equilibrium shifts to the left. Now, the next thing is how pH can potentially affect solubility. Now, if the substance has an active basic anion, like in this case, magnesium hydroxide, it has hydroxide. Clearly, hydroxide is related to pH. So if I play with the pH, in other words, I make it more acidic by adding an acid, that's going to react with the OH minus. H plus and OH minus form water. And what I'm fundamentally doing is I'm lowering the concentration of OH minus by adding the acid. So that's going to shift equilibrium to the right, making the magnesium hydroxide more soluble. So in a basic anion situation like this one, it's going to be more soluble in an acidic solution and less soluble in a basic solution. Now, if we had a reaction with an active cation, remember last chapter we got into, iron and copper and aluminum and other active cations. When we have an active cation, cations that don't come from a strong but come from a weak, those things are also active and pH will affect them. Now, in this case, it's going to be a slightly different situation. In that equilibrium system, the more basic it is, the more soluble it's going to be, because we have an active cation which is going to react with OH minus. So if we increase the OH minus in solution by making it more basic, that's going to lower the concentration of the active cation concentration, which is going to shift equilibrium to the right, increasing solubility. So therefore, making it more acidic would do the exact opposite of that. Now, where does this come into play in life? Well, you may have seen sinkholes in the news from time to time. They typically happen in places where you have limestone and a lot of acid rain. So you see this in Florida, you see this in Mexico, and potentially you could see it here as well because we've got limestone beneath our feet here. Limestone is calcium carbonate, and it's a low solubility substance, which means it stays as a rock, unless acid rain occurs. Because this is carbonate, CO3 2-. That's an active anion. And we just talked about how active anions are affected by pH. So think about what would happen to my carbonate if I added HCl. That provides a source of H+. That's going to react with the CO3 2-, forming HCO3- or potentially H2Cl3, carbonic acid. Well, that's reacting away the carbonate. As you lower the concentration of carbonate, that's going to shift equilibrium to the right, which means the calcium carbonate is more soluble. And if it becomes acidic enough, you can actually dissolve all of that limestone underneath your feet, creating a void, and that void can collapse. This was actually a factory, I believe, in Mexico that collapsed, and luckily no one was killed in this situation. There was actually one that occurred a few years ago while we were doing this chapter down in Florida. Similar situation, and there was actually somebody that it was their house and their bed collapsed into the ground, and that person was killed. So there are potential consequences to acid rain besides some of the ones you may have thought about. This is really dealing with solubility. Now, last thing I want to look at here is how the following ions would be affected by making the solution more acidic. Now remember, in an active anion situation, it's going to react with an acid, increasing the solubility. So what we're looking for here is active anions. Well, in nickel hydroxide, OH- is definitely an active anion. That's going to react with the H+, shifting equilibrium to the right and causing an increase in the solubility. Calcium carbonate. Calcium comes from a weak or from a strong, but carbonate comes from a weak. So that's another active anion. That's going to react with H+, once again lowering the concentration of the CO3 2-, shifting equilibrium to the right, and therefore causing it to dissolve more. Next one, barium fluoride. Barium's another inactive, but fluoride comes from HF. That's a weak acid, so that's an active anion. So increasing the acidity would increase the solubility of barium fluoride. The only one that doesn't is the last one, AgCl. Cl comes from HCl. That's a strong. So Cl is negligible in acid-base reactivity. So adding the acid isn't going to do anything to the concentration of the Cl-, and therefore you're not going to increase the solubility of the AgCl.